Hey, so again, it's going to be a very redundant lecture. So again, Marr's levels of analysis, we have the computational level, and here we're asking what is the goal of the system or the function? What's the system trying to accomplish, whatever that may be. Could be vision, it could be language, could be perception, depth perception, color perception, all kinds of things, right? What will You can also ask what will have been accomplished or completed after the system runs its course. What's the output of that computation or function? What should it look like, right? So, um, yeah. And then at an algorithmic level, you want to know what steps are taken to accomplish the goal. And essentially, you're saying, how does the system solve the problem, at least on an abstract level? What kinds of representations are created? What operations are performed? Uh, this level is more about like the actual process involved in an abstract sense, right? Not the physical process, but the conceptual process, I guess. What is the nature of the representations and the algorithm, right? So as I discussed in the intro lecture, some representations are easier to manipulate, and some algorithms are more difficult. Some algorithms are more, or sorry, some representations are easier to manipulate than others. Some algorithms are more conducive to different types of representations. And there may be different ways to solve a goal or different algorithms that could be used to accomplish a goal, right? You don't have to, for example, add two numbers the same way. I might add it the tens of two numbers, the tens places, right? So 40 plus 42 plus 63, I might add 40 plus 60, that's 100. And then 2 plus 3, that's 6, so 106. But you might start with the 2 and 3 and add that, so that becomes 6. And then you add 40 and 60, that becomes 100. And then you add those two together. So there's different algorithms or different steps that you can take um, to accomplish that goal. And the important thing here is, again, the important thing is at the algorithmic level, the explanation on an algorithmic level is supposed to be on an abstract level, which with often with very little reference to the physical instantiation or implementation of that algorithm. And then, at an implementational level, now you may ask, so what is what type of physical system is, what's the nature of the physical system that executes those steps, right? Is it a computer or is it a human mind, a brain, that kind of thing. Uh, you could also ask what brain regions are involved, how are the steps executed physically, that kind of thing. Okay, now we'll talk about one simple example to talk about Marr's levels of analysis. The goal, hopefully, is to understand the difference between the algorithmic level and the implementational level, and how maybe the implementational level is not as important as maybe some students think it would be. So I'm going to start with something. I'm sorry, what are the physical processes? Of course. So those are the questions. Now we'll start with the chess example. So we'll talk about chess, right? So what's the goal of chess? When you play a game of chess, the goal is to put your opponent in checkmate, right? And that means that the king has nowhere to move safely, right? Without getting captured, right? So of course, understanding uh, chess on a computational level requires you to understand what checkmate is, the rules of the game, the pieces of the game, and how pieces can capture other pieces, that kind of thing. But all of that information would be relevant to the explanation of chess on a computational level. Uh, Whereas the algorithmic level is about, how do you win? What is the solution or the specific steps or strategies to to go from the initial configuration of the chess pieces to checkmate, so that's your input and output. And, so yeah, for the algorithmic level, is there an algorithm that can achieve this goal, right? So if you were to program an algorithm, you might have a series of if statements So if the configuration looks like X, whatever that configuration looks like, and your opponent does Y move, then you might do this new move, right? If they do this Z, if they move like this, then you should do this other move, etc. That would be sort of the algorithm or code programming that would be involved, the steps that would be taken to get from the initial configuration to checkmate. Of course, this, maybe you would have a large decision tree that shows all of the possible sequences of moves that you and your opponent could make. And then you might follow the path that maximizes your chances of winning. Of course, you probably wouldn't do this because we know that probably humans don't do this because it's an enormous astronomical number uh, of steps that you can make, sequences, paths of on the decision tree of how to move your pieces. So you probably don't do that. But that's one example. Um, and then for the implementational level, right? Now here's where I'm hoping that it becomes obvious that maybe the implementational level isn't that important, right? So what are the pieces made of? Are they wooden or are they metal? Are you playing on a computer or are you playing with people as are you playing with people as your pieces, right? Um, Again, and also really good chess players don't even need a physical board. They can play each other in their head while visualizing the board and updating that visualization after each move. But the important thing is that you can still, it doesn't really matter if the chess pieces or the chess board are made of wood or metal. It doesn't really matter. The game is the game. The rules are the rules. The algorithm that you take probably doesn't matter. Or sorry, the whether it's made of whether the pieces are made of metal or wood probably doesn't matter on an algorithmic level. The algorithm's the same regardless. Okay. And similarly, it could be that the idea is that the brain implements the rules of the mind, but maybe a computer could do it, for example, or some other system that's not like a brain could do it. Okay. Okay. In the next video, we'll talk about more examples as it relates to color vision. That'll be the first one.